What's up guys and girls, Raj here, back with another Kubernetes question answer video. For those of you who are new to the channel, my name is Raj. I'm a principal specialist SA for containers and serverless at AWS. I'm also a best-selling author, public speaker, and a YouTuber. Just a gentle note, I am currently at 99,000 subscribers in YouTube. So if you found this video helpful, please subscribe and get me over the coveted 100,000 subscriber mark. Questions we are going to cover today. Tell me some challenges of high-scale Kubernetes cluster. High scale as in both on the size of a cluster where you are running thousands of worker nodes as well as with high scaling requirement. How do you enforce deployment YAML best practices such as specific registry usage, everyone should use request limit, etc. How do you reduce cross availability zone traffic cost? Give me 3 design implementation of Kubernetes that you have done. How will you implement disaster recovery for Kubernetes? How will you optimize Kubernetes cost? How would you provision a Kubernetes cluster with AWS practices built in, such as security best practices, reliability best practices, etc. I have provided the timestamps for your viewing convenience, so you can jump to the question that you want to know the answer of. All right, learnings of hyperscale. Interviewer gonna ask you this question to see if you actually worked hands-on in a Kubernetes cluster in production. All right, let's go through it. One of the challenge that customers face with running a hyperscale Kubernetes cluster is IP address exhaustion and latency of obtaining IP addresses. So whenever it comes to scaling, there are 2 things. One is how far you can scale, like how many pods, which is how many IP addresses, as well as the burst, how fast can you scale and can your cluster keep up with it. The prefix assignment is to deal with the latency. So every time your EC2 worker node needs to grab an IP address, it's called EC2 API to grab one at a time. Using prefix assignment, you kind of get a chunk of IP addresses ready to go, assigned to your ENI of the EC2. And when your pods scale up, each pod has its own unique IP address. It can just grab from that warm pool of IP addresses. Second is to deal with the IP address exhaustion itself. If your subnet runs out of IP addresses, you can add secondary CIDR. However, in cases where the project runs out of IP address itself, if you add a secondary CIDR, that means you have new IP address ranges. If you do not have that, you can reuse the same overlapping IP address range in different VPCs. So you can reuse IP addresses. This is a very, very popular technique amongst production customer Kubernetes cluster. In this technique, you use the overlapping non-routable CIDRs to run your pods. Each pod gets its unique IP address, and the pod networking is separate from the host or EC2 networking. So EC2s can run in one subnet, but the pods running inside the EC2 can run in a different subnet. I know this part is a little confusing. What that means is EC2 will run in, let's say, subnet A, but the pods running can get the IP address from another subnet. And that subnet could be non-routable and overlapping. Now, a quick note, I'm just giving you the answers because I work with production Kubernetes clusters, right? And it's good you study them and the interviewer asks you, you answer. But make sure you study further so that when the interviewer asks you a follow-up question, you know how to answer them. So I'll give relevant study links for you to study up, especially this overlapping non-routable CIDR one. Last solution to deal with IP address exhaustion is use IPv6. You get way more IP in IPv6 than IPv4. If you give this answer, be prepared to get the question that, okay, what are some challenges or considerations to adopt IPv6? Okay, the next learnings are, if your workloads needs to scale up very fast, or let's say a telecommunication company is releasing a new iPhone, and millions of people are gonna try to buy it at the same time. So not only the limit of scaling is necessary, but you need to scale up very fast. So the traditional cluster autoscaler, which scales the EC2 nodes, could be a little slow during traffic burst. AWS Carpenter is better performant. Generally, AWS Cluster Autoscaler spins up EC2 nodes in minutes, and Carpenter spins in seconds because Carpenter does not need to go through autoscaling groups. It can directly call EC2 APIs. You can also use Cluster Over Provisioner during critical events. With Cluster Over Provisioner, you spin up a bunch of EC2 worker nodes with pause pods in it. So basically, EC2 nodes are up and running, and as your real application pods are scaling up, they can replace those pause pods on the EC2 node and handle the incoming burst traffic. And also, there are some add-ons which struggles when you go beyond like hundreds of nodes, right? If you are running thousands of nodes, which is one of those add-ons is Core DNS. So you need to scale Core DNS, and you do that using proportional autoscaler. So with proportional autoscaler, Core DNS will scale based on the number of EC2 worker nodes. So even when you are running thousands of worker nodes, you won't see any throttling of traffic. Next is related to logging. There are two popular logging agents. One is FluentD, another one is FluentBit. FluentD has more plugins, as in it integrates with more services and logging platforms, but it is very clunky. It takes more memory and it is slow. FluentBit is written in Ruby and it is much faster than FluentD. So the suggestion would be to switch to FluentBit. Also, remember, if during the huge burst of traffic, FluentBit will produce a lot of logs, but your logging backend, maybe Splunk or CloudWatch, they may not be able to keep up with this rate of incoming logs. So in that cases, what you can do is use some streaming service in between. So FluentBit can put all the logs in a Kinesis data firehose. So basically FluentBit can put as much log as it can, but the logging backend does not need to consume those logs at the same rate. Because it is saved in Kinesis data firehose, logging system can consume based on the rate it can do it. The last one, you probably have that in mind, is always cost when you are creating or managing a hyperscaled Kubernetes cluster. The cost is a factor. Again, if you answer this, be prepared to answer how would you reduce the cost. And I have a separate question on it, so we are going to cover it as well. Couple of quick plugs. All my best-selling and highest-rated Udemy courses are on sale this week. You can go to www.cloudwithraj.com, and under top courses, you can simply click this discounted Udemy link and it will open up the Udemy course with maximum discount already applied. This will expire in next 5 days. Another quick announcement, if you want to get the slides for this video along with some additional study material and some additional tips, sign up for my newsletter. So you can scroll down the same website and just put your email and sign up. I'm going to send out the slides of this video in next couple days. Buying my courses is a great way to support me and this channel. All right, back to the video. All right, next question is, how would you enforce policies? For example, you have a repository from where you want your container images coming from. And if someone tries to pull or run a container image in your deployment file, which is from a different repository, you should be able to reject it. Another good practice is every application should specify a request and limit. So this is to ensure that your pods don't take up way too much CPU and memory and then end up spending a lot more money. So how do you ensure that every deployment file or pod specification file has that request and limit? And these are a couple examples. There could be others. So you do that using admission controller. So if we look at the flow of the Kubernetes API server, so basically starting from the command when you run kubectl apply -f deployment.yaml, and then to the deploy to the cluster, there are multiple phases. When you run a kubectl command, it goes to the Kubernetes API server, which goes through the API HTTP handler, and then it checks the authentication and authorization. So the user that you are submitting this command as, it is going to check that if you have access to do all the stuff that you are trying to do in deployment.yaml. Then comes the important part, which is the admission controller. There are two steps to it. One is the mutating admission controller. With this step, the manifest file can be updated. I'll give an example. Let's say you are deploying something, deploying a pod. If you do not specify a namespace, that pod gets deployed into the default namespace. But Kubernetes does not know, right? So this mutating admission controller actually modifies your manifest file and adds the namespace as defaults. It adds the service account as default, etc. Now, as part of this, you can also define certain things that it can add in addition to the default ones, right? And they are called through webhook. And then comes the schema validation, where the schema gets checked. And then another admission controller phase, which is validating admission, which can check certain fields and then accept or reject the deployment file. I think you got the idea. Here also you can call webhook, and you can use open policy agent such as Gatekeeper or Kyverno, where you can define policies to check. So you can implement policies which checks which registry the container image is coming from, or whether the deployment file has request and limit defined. And based on that, you can accept or reject. If everything goes fine, deployment file is written to etcd, and then based on the reconciliation loop, they gets deployed to the cluster. All right, next question. How do you reduce the cost of cross availability zone traffic? So this is a typical EKS cluster implementation, right? You have a couple of availability zones, public subnet where your EC2s are running, and then a private subnet where your database is running, and you have application load balancer as ingress. And then your pods running inside this EC2, and then the traffic comes. The traffic from application load balancer to any availability zone does not incur any data transfer charges. So these are shown by green arrows. The traffic that stays in the same availability zone from the pods are free of transfer cost as well. The pod to database on both sides on the same availability zone, free of charge. However, the cross AZ traffic from pod to pod or pod to other AWS service incurs traffic charge. And there is a small charge for the traffic for application load balancer egress, so basically from ALB to outside of the VPC, but that one is minimal. So this is important, especially the red arrows. If you have a chatty workload or analytics workload, or if you have a service mesh running, there could be a lot of cross availability zone traffic, and they will show up in the bill. So how would you reduce that? For high pod-to-pod data transfer workloads, utilize the availability zone specific label. Each node that comes up will have a label attached. Now remember, label is not same as tags, right? Tag is an AWS concept, label is a Kubernetes concept. So with those EC2s, there will be a label called topology.kubernetes.io/zone. It will be like AZ1, AZ2, etc. And you can use those labels to schedule pods using node selector and node affinity. So if you know a workload is very chatty, you can specify deploy at the same availability zone. Now the question will be, if you do that, your application no longer remains highly available. Now remember, your traditional microservices, they should not be incurring too much cross-AZ cost. You only do this where pod-to-pod cost is high, such as analytics workload. And generally, analytics workloads comes up, do the job, and come down. So it's okay for them to run in one availability zone. Now with Cluster Autoscaler, you can create managed node group in same availability zone. So all the EC2s will come up in one AZ. That way, all the pods will be in the same AZ as well. With Carpenter, you can define specific availability zones in the provisioner itself. So all the EC2 nodes will come up in the specific AZ. With Kubernetes upstream version 1.24 and beyond, you can enable topology aware hints. So this will be very useful for service mesh. With topology-aware hints, Kubernetes will try to keep the traffic within the same availability zone where possible. So I'll give a link to it, so study up on it if you plan to mention it in the interview. If you have not done so yet, please click that subscribe button, get me over that 100,000 subscriber mark. All right, next question. Tell me about 3 Kubernetes design. Well, the one design, which is very, very popular, is microservice, right? You have the application load balancer as the ingress, you have pods running, and then you have databases, and basically the ingress is working as the face of the microservice, and the traffic comes. So study up on it. I have a bunch of other videos on it as well. Second one, you could say, is a Kubernetes badge job. So this is a sample manifest where the kind is job, right? And you could also mention how many parallel copies of your job can run. And then you could do a restart policy and then a container. The next Kubernetes design, mention this if you want to set yourself apart from the crowd, is event-driven with Kubernetes. Oftentimes we see that customers want to adopt event-driven services which are serverless to get all the benefits, but they want to keep the business logic in Kubernetes. So this is one of this design where we are using Event Bridge, because Event Bridge has a schema validation, and then based on the values on the message, it can invoke different endpoints, it can replay, it has schema registry, it has a lot of good advantages. And what it's doing is, all the business logic is on the right side on Kubernetes, and Kubernetes pods can be invoked using application load balancer as the ingress. However, there is a twist here. You would say, what is this Lambda doing? If the application or this application load balancer is internet facing, so this ALB will be associated with public subnets, then you do not need this Lambda, then Event Bridge can directly invoke the application load balancer. But in a lot of cases, the applications are internal facing, so they can only be invoked from paired VPC or data center, which is direct connected to the VPC. In those cases, the application load balancer will be internal facing. So in that case, you need a Lambda. So the message is coming to the Event Bridge, and then based on the Event Bridge rule, it invokes the Lambda, and that Lambda is just a relay, which is just sending the message to the application load balancer, working as the ingress, and then ALB calling the EKS. And then it's using secrets manager through VPC endpoint, that part, so that the traffic doesn't go through internet. And then we have set up SQS dead letter queue for the Lambda in case some messages fail to get processed, you can reprocess them. All right, next question, how do you achieve Kubernetes disaster recovery? This one doesn't get talked a lot, but in all real world Kubernetes cluster, this one is considered very critical. All right, so this is how your typical cluster looks like, right? Couple of availabilities on, which is good. That means your application is highly available. You have EC2s running, and then you have pods running inside those EC2. And using topology spread, you can ensure that you have pods for the same application in different availability zone. And then you have the application load balancer ingress. Okay, so this architecture is in one region, right? And this is, even though it's highly available, but if the whole region goes down, then your application goes down, which you do not want. Most cases, for critical applications, customers want the application in another region. So how do you do that? You do that by replicating the same architecture in another region, region 2. Now you have 2 application load balancer for each of this region. So you need some intelligence to route traffic to the region which is up, right? So how do you do that? You do that using a DNS service such as Amazon Route 53. You can use a failover routing. So in case one region goes down, the Route 53 will automatically start routing traffic to the healthy region. Now there could be a little delay because Route 53 cache some health checkup results. So if you want even faster routing, you can use a newer AWS service called AWS Global Accelerator, which instantly fails over to the other region. Now this handles the Kubernetes application part, but whenever you talk about disaster recovery, always think of different components. So the application part is good, but how about the persistence layer, which is the database part? So for the database part, you have to do database replication. So in case you are using Amazon RDS, you can use the out-of-the-box replication that AWS provides. If you are using some other database, you either have to orchestrate the replication yourself or use some third-party solution. Let's say you have a stateful application. So in case your pods needs to use some EBS volume, so you can replicate that and take backup of that using tools like Velero. Now the interviewer will ask you, if you run the same cluster in two different regions, your cost will be astronomical, right? Because some of this application could be huge. So you have to tie your answer back to different AWS DR strategies, which is backup and restore, pilot light, warm standby, and multi-site active-active. So you could say that multi-site active-active is the most expensive. So you could do that for very, very mission critical applications. But generally, an acceptable standard is warm standby. So if I go back to the previous picture, so even though the cluster is running in two regions, the region 2 is running in much smaller scale. You have to use horizontal pod autoscaler and Carpenter or cluster autoscaler. Because there is no traffic going to region 2, the number of pods will be much smaller. So don't use just a fixed number of replicas without scaling, right? That would make your cost very high. And as soon as the traffic starts flowing, the horizontal pod autoscaler will start scaling the pods, and then it will ramp up. How do you optimize Kubernetes cost? This is also tied to the learnings of hyperscale. If you run a big cluster, the cost will be a critical factor. You have to demonstrate that you understand the cost components of a Kubernetes cluster. Don't just talk in general terms like, oh, Kubernetes cluster is expensive or Kubernetes cluster is cheap. You have to say that Kubernetes cluster cost is divided into two main components: control plane cost and data plane cost. The control plane cost is the Amazon EKS service cost, which is fixed, 10 cents per hour, which is very cheap. And the good thing is, even if your cluster scales up to thousands of nodes, that cost does not change. AWS will scale up your control plane as needed and handle the higher capacity cluster. Data plane cost is broadly divided into three main categories: the workload cost, which is the cost of your pods, container, running inside EC2, so the compute cost based on CPU memory, either for EC2 or the AWS Fargate, and also it's tied to auto-scaling. You can also incur network cost. We talked about this in the previous interview question. Go ahead and check it if you have not. So the network cost could be the pod data transfer cost, cross AZ, Amazon ECR, transfer cost, elastic load balancing cost, NAT gateway cost, etc. You could also incur observability cost, cost of logging, like saving the logs, the cost of running the agents, as well as the monitoring cost. Now, not all of these costs are same. 70% average of total cost is on this compute. So the interviewer will be interested to know more about how would you optimize this compute cost. All right, so how do you optimize the compute cost? Mention a sample pod specification file. So in this pod specification file, under requests, we are allocating 512 megabytes of memory and 250 millicore of CPU, and then we have some limits. The requests is the important part. What that means is, throughout the life cycle of this pod, it is guaranteed to reserve 512 megabyte of memory and 250 millicore of CPU. Memory is not a compressible resource, so if your pod runs out of memory, it will terminate. However, CPU is compressible, so if your pod needs more CPU and it goes beyond the limits, it will throttle, but the pod will not die. So it is important to allocate a optimal amount of memory and CPU in the requests. However, most of the times, developers allocate way more than needed. Now the problem here is, since the pod will reserve the requested amount of memory and CPU throughout the life cycle, you end up spinning up more EC2s to accommodate these bloated pods, and you end up paying more money. So the best way to save cost is to optimize these requests and limits. How do you do that? You can use a software like KubeCost. Now KubeCost is a licensed product, but if you are using with Amazon EKS, you get it for free. Not many people know that, so mention this. If the company wants to use open source products, there are products like Goldilocks, Kubernetes Resource Reports or KRR, etc. So this is a sample dashboard of KubeCost. Again, you get this for free if you are using EKS. It shows that you could save up to $518 per month, cost efficiency, etc. And more importantly, it shows which areas you can save cost. And then you could see this right size your container requests. And it shows that for each pod, how much memory and CPU you allocated and how much you are using. Again, you don't pay based on how much you are using, you pay based on how much you are allocating, right? So it kind of shows based on the usage that you can save this much money and you should reduce the CPU and memory to these numbers. All right, the last question is, how do you provision a EKS cluster with EKS best practices built in? If you think about Kubernetes cluster, you spin up a cluster, then you go implement different best practices, you install different add-ons. Now, EKS Blueprints is a new open source project where AWS gives you the infrastructure as code to create complete EKS cluster that are bootstrapped with the add-ons that you need, as well as some best practices built in. An EKS Blueprint comes in two flavors, Terraform and CDK. So Terraform is the more popular one to provision EKS cluster. If I go to the examples, so you can see on the left, these are all the examples. For example, if you want to provision a fully private cluster, you simply click this fully private cluster and then you run this Terraform init, Terraform apply, and then it will create the fully private cluster with the best practices built in. Similarly, one very common use case we see is multi-tenant cluster, where there are multiple teams running in the same cluster. This blueprint creates multiple namespace as well as it provisions like the request quotas for each namespace, so one team cannot take over the resource for the whole cluster, as well as service accounts and RBAC roles for each of those namespaces. Similarly, if you want a cluster with the Carpenter add-on built in, if you want an Istio multi-cluster, IPv6, etc. And remember, EKS Blueprint is open source, right? So not everything will be matched 100% to the requirement of the company. So you can grab these blueprints and then you can change it as you see fit and then incorporate in your own CI/CD pipeline. All right, folks, if you have other questions that you face in your interview that you are not sure how to answer, ask me in the comments. If you like this video, if you found this video helpful, please click that like button, smash it if that's something you are into, subscribe, buy my courses if you want to support me, maximum discounted link in the description. That's it for this one. I'll see you guys and girls in the next video. Bye.